Okay, let us talk about the second part of the propagation of the signals in optical fiber. So when the fiber is bent, so there is quite a loss which is happening. So radiation loss due to any type of bending, and you can bend the fiber in such a way that it has got a radius of curvature above which, if it is bent, there is a possibility of breaking or any other signal might be lost. So radiation due to loss of bending of energy in the fiber at at the uh, at that particular radius of curvature wherever it is bent, if it is exceeding certain angle, so we'll call it as critical angle or the radius of curvature. If it is forming a circle, if it is forming a circle, then it is going to be called as a radius of curvature, and it is going to let the light go out of the fiber. So radiation attenuation coefficient can be given as alpha r c1 exponential of minus c2 into r, where r is the radius of curvature, c1 and c2 are the constants. We'll solve further problems on this. So this is what the cladding and the core looks like, and this is where the fiber is bent. So how much it is bent is dependent on the radius of curvature. So there are two types of bendings, micro bending and macro bending. As this is seen, it is very minute in nature, very small order, and here macro bending is usually intentional bendings, and there is a possibility of signal loss in this case also. So multi-mode fibers have got a different radius of curvature, and single mode have got a different radius of curvature as well. So critical radius RC, how much it can be bent in such a way that it can avoid any signal loss. RC can be given by this particular equation: 3n1 square lambda divided by 4 pi in difference of n1 and n2 square, 3 by 2. So which can be estimated. It may be observed that the expression given in equation, that potential loss may be reduced by, we can use this particular equation to understand the design fiber with the large refractive index difference. If it is high, then that means radius of curvature can be reduced. Operating at shorter wavelength means radius of curvature again can be reduced. So this is one possibility. So taking into consideration of the single mode fiber RCS, here it was RC, please note it is RCS. So this is quite a bigger equation where we need to find out lambda c, where lambda c is the critical wavelength. So lambda c can be given by 2 pi a n1 to delta to the power 1 by 2 divided by 2.405. So this is one thing which you need to calculate extra when it is single mode fiber. Let us solve a problem where two step index fibers are used. One is multi-mode and the other one is single mode. Let us consider both the cases. So multi-mode fiber with the refractive index of the core as 1.5 and relative refractive index difference, that is delta, given as 3%, and operating wavelength is 0.82 micrometer. So calculate the radius of curvature for this. Let us calculate. So we need delta. So delta can be calculated by n1 square minus n2 square divided by 2 n1. So with the help of delta, which is already given as 3%, so substituting that, we will get cladding refractive index, which is equal to 2.115. So you have core refractive index, you have lambda, you have n1 and n2. You can calculate radius of curvature. I have not calculated here, but you can go ahead and calculate it with the direct substitution. You have n1 as 1.5, n2 as 2.115. That is the n2 square. We want n2 square, so I've directly given it, kept it as n2 square. So you can calculate with the help of lambda, which is equal to 0.82 micrometer. Please do not forget the micro here, otherwise you might land into trouble. And finally you get the radius of curvature for multi-mode fiber. Let us talk about single mode fiber. 8 micrometer core diameter. So we have the core diameter given, it is not the radius, so please mention, you have to write it as 4 micrometer. And single mode fiber core refractive index, relative refractive index difference as 0.3. Here it was given 3, here it is 0.3. Operating wavelength is different, 1.555 micrometer. So let us calculate again n2 square. Here the n2 is different because the refractive index is not 3%, it is 0.3. So you have to do a small change. So you have one more extra 0 here. So that is what is calculated. So n2 square will not be 2.115, it is 2.237. So calculate lambda c as I have told it in this case. So you need to calculate lambda c before you substitute this lambda c here. because the rest of the values are already given. So calculate lambda c 2 pi a n1 2 to the power 2 delta to the power 1 by 2 divided by 2.405, which is a constant there. So you calculate lambda c and find further substitute lambda c here and lambda here, and the rest of the values you get RCS. So this is the value of radius of curvature for single mode fiber. So calculation of radius of curvature for both the cases is very important. This is the same formula again. So based on the radius of curvature, we can get to know what type of fiber it is used. So based on to find the cutoff wavelength for step index fiber to exhibit the single mode operation when n1 is equal to 1.46 and core radius is 4.5 micrometer, assume lambda is equal to this. So lambda c you calculate, and then you can understand that this is the value is less than 2.405. So this you can tell that if V becomes larger than 2.405, it is not single mode fiber, it is multi-mode fiber. Remember that based on the value of V, based on the value of frequency, we can understand if it is less than 2.405, it is a single mode fiber. Next comes dispersion. Dispersion is broadening of light of the transmitted optical signal caused due to distortion for both digital and analog signals. Cause broadening of the transmitted light pulse. Whatever the pulse is, it is going to be broadened. We have seen scattering, we have seen attenuation, we have seen other type of signal loss, bending loss, but this is a different type where the pulse is going to be broadened. So it broadens and overlaps. So this is where you consider the intersymbol interference, ISI. So two signals can be misjudged as one signal, or one signal can be misjudged as two. So there is a possibility of both. So this is what it looks like. So here if you can see 1011 is supposed to be sent with an amplitude perfectly before sending. So once it has transmitted the fiber output at the distance L, so this 1 is going to be having a delay, and this is 0 and this is 1 and 1. So here there is no much of a difference, and this is where the symbol interference, and then fiber output at a greater distance L2, which is higher than L1. So this is where it is completely overlapping on the neighbor's signal, and hence we call it as ISI. So for non-overlapping of light pulse down on an optical fiber link of a bit rate beta t can be less than or equal to 1 by tau. Tau is the pulse duration, half of the pulse duration. So this is how much the broadening happens. Alright. Okay. Next, coming to different types of fibers, we have multi-mode step index fiber, we have multi-mode graded index fiber, because here it is N1 here, that is core, here it is N2, but here N2 and N1 keeps on varying. Remember that in multi-mode step index fiber, we do not have a problem. Here we have a small grading. Okay, so here even though it is a small grading, but still I'm going to take N1 and N2. This is what the core and cladding looks like, and this is the amplitude, and this is the multi-mode, and this is the multi-mode is itself, but there are only two modes. Here there are four modes which are used, and here single mode step index fiber. This is what the output pulse looks like. So it is better to use single mode fiber when you have to use or retain the amplitude for a further range. Next comes one problem where multi-mode graded index fiber exhibits a total pulse broadening of 0.1 microseconds. Pulse broadening is given, and pulse broadening is tau, and for a distance of 15. So maximum possible bandwidth on a link, assuming no intersymbol interference, pulse broadening per unit length, and bandwidth length product of the fiber. So you can calculate the pulse dispersion per unit length can be calculated by 0.1 micro divided by 15. 0.1 micro was available here, and BT is equal to 1 by 2 tau. 2 tau is this value. You are going to multiply this with 2, and you are going to get the maximum output bandwidth, which is given by 5 megahertz. So second one, pulse broadening can be given by 0.1 micro divided by 15 from the formula 15, and it is coming up till 6.67 nanoseconds per kilometer. 15 is the length. 15 is the length. So whatever the pulse broadening you have divided by 15 will give you pulse dispersion per unit length. Next, they've asked bandwidth length. It is not per length, bandwidth length product of the fiber. So you have to calculate bandwidth multiplied by length 15 into 5, which it directly says the bandwidth into length product of the fiber. So bandwidth was the previous case A, and the length which is given as 15. So here you have 75 megahertz kilometer. It is not per kilometer. So alternative, it can be found out as B output divided by multiplied by L is equal to 1 by 2 into whatever the value of dispersion you had. You are going to substitute it here, and then you are going to get the same result. So you can use any alternative approaches. Next comes chromatic dispersion. Chromatic means based on the color. Chroma means color. Variation in the phase velocity of light according to the wavelength. So depending on the wavelength, there is a broadening of signal, and that results in overlapping and ultimately errors. So if you have blue color signal and the red color signal, there is a possibility that even though it is starting at the same time, after a while there is a possibility that red signal might be facing a delay, and after certain longer distance, there is a possibility that the red does not reach when blue reaches the top. So this is what happens before transaction, and during reception you have ISI. Dispersion is the time domain spreading or broadening of the transmission signal light pulse as they travel through the waveguide. Next, coming to the chromatic dispersion, and there is a very important derivation here of material dispersion. So dispersion which is happening because of the material, whatever the material we are going to use is the waveguide. So pulse broadening due to material dispersion results from different group velocity. We have different group velocities, as I already explained in the class. What is the group velocity and the phase velocity? Group velocity of the various spectral components launched into the fiber. Different spectral components are going to be released onto the waveguide. So the group velocity of the components are going to be different. So how can you calculate? We are going to differentiate the beta, that is the propagation constant, with respect to angular velocity. So angular velocity, angular frequency. So dB by d omega will give you tau g, or the group velocity. So you can calculate simple calculation. Tau is the time and this is the frequency. Time multiplied by frequency will give you a constant. So tau g d beta by d omega will be using this equation. 1 by c. C is the speed of light. N1, N2, you know whatever the value of N1, and lambda. So this is the expression for tau g. So you have to remember this. And secondly, where N1 is the refractive index and tau m is the material dispersion. So here the expression for material dispersion can be given by L by C. L is the length of the fiber which is used, and this expression again. So same thing we are going to use. So tau m is nothing but L into tau g. So these two equations you need to remember. So after that you are going to expand it with the help of Taylor series, where sigma m is the material dispersion which we need to find the expression for. So sigma m can be given by sigma lambda and this expression. So we are going to leave the higher order derivatives. We are going to keep only the lower order derivatives. So this can be equated as this approximately. So the material dispersion can be given by sigma lambda, which is the spectral width. Please remember, this is the spectral width, this is the material dispersion. So spectral width derivative of tau m, which is the pulse delay. So derivative of pulse delay divided by d lambda will give me material dispersion. So what you are going to do is, we are going to differentiate tau m with respect to lambda and substitute it here, and multiply by sigma lambda so that we can get this particular value. So let us see how it is going to happen. So we are going to take the previous case of tau m, tau m. I'm going to differentiate tau m with respect to lambda. Tau m with respect to lambda. So L by C, I'm going to keep it as it is, and n1 differentiated with respect to lambda will give me dn1 divided by d lambda, and this follows the UV rule because lambda into dn1 divided by d lambda will become second order derivative. So that is what is happening here. So L, I have taken it outside because it is going to be common for everything, and then UV rule will tell you dn1 divided by d lambda into d lambda by d lambda. D lambda cancels out, and once d lambda cancels out, once d lambda cancels out, you will have the expression which is going to be in this way. So further simplifying it, d tau m by d lambda will give you this value, and in order to get the material dispersion you have to multiply by signal spectral width. So spectral width sigma lambda I'm going to multiply, and I'm going to write it in a modulus signal because I do not want the negative symbol here. So this is what the expression for material dispersion. So sometimes it is quoted that lambda square multiplied by second order derivative of n1 with respect to lambda can be given by and written as m. So 1 by L d tau m by d lambda. So this is what I'm going to rewrite. So lambda by C and second order derivative, I'm going to leave it as it is. So m can be expressed as material dispersion parameter and can be written as it is okay if you are writing m in terms of this, not necessary that you have to write it in this. So which is expressed in picoseconds nm per meter per kilometer. Alright, so this is what the material dispersion expression is. So all you have to do is remember this and this, substitute this after derivation, remember the Taylor series. So you are going to get 1 by L d tau m by d lambda, and hence this expression. Lastly, you have waveguide dispersion, the dispersion which is happening because of the waveguide. So it is caused by the power distribution in the fiber's core and cladding, which is the wavelength dependent. Light travels faster in the core and slower in the cladding. Different power distribution cause different wavelength, travels in different speed. We can change the fiber refractive index profile to achieve different waveguide. Remember that the light travels faster in the core because of the higher refractive index and slower in the cladding. And finally, intermodal dispersion, how different modes create the dispersion. So pulse broadening or the intersymbol interference due to intermodal dispersion happens, results from the propagation delay. As I told you, there is a blue car and the red car. It is not going to reach the destination even though it is in the same starting point. Differences between the modes because of the difference in the lambda, that is wavelength. As the different modes which constitutes a pulse in a multimode fiber travel along the channel at a different group velocity, the pulse width at the output is dependent upon the transmission time of the slowest and the fastest mode. So remember that when we are talking about different modes, the pulse in the multimode fiber travel along the channel at different group velocities. So the possibility that all the red signals might not align with the blue signals or any other colors. So this is where we come to an end of intermodal symbol dispersion, waveguide dispersion. Remember, this is a very important um, expression which you need to remember and derive. Alright, thank you so much.